Alright, so welcome to my presentation today. So, when I was growing up, the coolest room in my house was my dad's room. And it was full of model trains. He had a wall of 70s science fiction and the like. So whenever I was a little kid, I'd always go off and try to explore his room. Well, one day when I was 9 years old, I happened across his mineral collection. And in there was this. One lovely little purple fluorite octahedron. And that instance got me hooked on minerals and why I'm here today. Not only the weird shape, I mean, how often you see an octahedron around, but I just love the intense purple color. It's now part of my collection. And that has continued throughout my entire love of minerals, because I love all minerals, yeah, but I love colorful minerals more. So, especially if it's got any sort of color effects, that's my jam, and that is why I'm here today. Oh, I don't know if you know this, I should probably introduce myself before I forget. I am obviously a member of the club. I am an earth science teacher with Commonwealth Charter Academy, an online cyber school. I actually wonderfully got to teach earth science this year, and we'll be doing so again next year. So that's my background, and yeah, minerals. So, where does color come from? Well, it's a color that we see is an interaction between two things. Of course, you've got the mineral, but you also have light. And this is the full spectrum of light. And as you can see, the part we can see that is just this teeny little band here, the visible spectrum of light. It goes on far above and far below the visible spectrum of light. Now there are some living things that can see these other spectrum. For example, some insects can see ultraviolet. And there are some predators, like snakes, that can see into the infrared or heat energy. But for the vast majority of us, we are stuck with the visible light spectrum. So I'm going to divide this into three parts. First, we're going to talk about chemical color. The color that comes from the makeup of the mineral, the chemical compounds inside of it. And so, originally, I'm sure you've all heard this explanation before, color, we have light shining on a thing, most of it gets absorbed, the stuff that bounces back to your eye is what you see. That's good enough, but it's actually quite a bit more complicated than that. Now that being said, do note I will be trying to keep this around a high school level, so we are going to touch on quantum physics, so please do not go running for the door. I know how difficult quantum physics is. I had a full semester of it in college. It was not fun. But I will make it more accessible for a layperson. So, again, we're talking about chemicals, we're talking about compounds, and to deal with them, we need to talk about atoms. And unfortunately, this here is the atom that everyone knows and loves, but it's wrong. And it's been wrong for about 100 years or so. So we don't have electrons orbiting like little planets around a nucleus. It's a smidge more complex. It's just that got memeified and is what everyone knows. So this is an actual atom. We have our super tiny nucleus, and that's big for a nucleus, by the way. And around that nucleus, we have things that are known as orbitals. So each of these lobes that you see there is an orbital. Orbitals are literally physical spaces that you can stick electrons in around the nucleus of the atom. And electrons, they generally are down by the nucleus, because that's the most stable position It's the least energetic, that's where they want to be. But they can move between orbitals. And fun fact, when they're moving between orbitals, it's literal teleportation. They wink out of existence in one orbital and wink into existence in the other orbital. They do not travel across the space in between. And if that sounds weird, you're right. It is weird. We don't know why that happens. In fact, if you can figure that out, you've got a Nobel Prize with your name on it. Guaranteed. So anyway, how do we get electrons to move? We zap them with energy, most of the time in light. So we take light, we smack the electron with it, and it goes to a higher level orbital. And actually, interestingly enough, you can tell the energy that we used, because you must hit it exactly. You might think that, oh, if I hit like double the energy, it'll just go higher. Not necessarily. Unless your energy level matches the orbitals, it won't go. It's one of those weird things. So anyway, light energy comes in, smacks electron goes up. Then, when the electron falls back down, back to a lower energy state, it releases energy as well, and that energy is equal to the difference between the two orbitals. Most of the time, it also loses energy. Why? Electrons are physical items. We had to move a physical item, therefore we used energy, and so that energy gets used up. So we always lose a little bit of energy as heat. And when that happens, basically the light that is emitted falls out of the visible spectrum and is infrared or heat energy. So again, as you can see, the visible spectrum here is not very big, so it doesn't take much to have the light energy drop out of the visible spectrum. Now we actually see something fairly similar when we see fluorescence, where we take the higher energy light, smack something with it, and then it drops in energy from ultraviolet, which we cannot see, to the visible spectrum, which we can see. So basically, fluorescence is electrons going up, electrons coming down, emitting visible light. Phosphorescence, on the other hand, is pretty much the same thing, except with more steps. So electrons get hit by light, the electrons go up, but they can't go back down straight away. Instead, they go through lots of other transitions before it can finally come back down. And all of these transitions here take time, and actually they can add up to having a time lag that we can physically see, which is kind of amazing. You're literally seeing transitions from electrons. So anyway, the key point is we're taking light and we're removing it from the mix that we see. Because again, the light that's transitioning these electrons is being released as heat. We can't see heat, and so basically we're subtracting that light from the light we see. And when we do that, that has an interesting effect. So if we're subtracting one type of light, that will mean that its complementary color appears more vivid. We'll see it more of. So if we're subtracting orange light from our light mix by the electrons, the object will seem more bluish. So a lot of the colors we see are solely because of a subtractive effect, because of the electrons moving about in the atoms. And remember, all of this deals with one electron. There are, tens to hundreds of these electrons around atoms, and then you bond them together to make even bigger orbitals, even simple molecules like sugar has like 30-ish atoms in them, all bonded together. So as you can see, it gets complicated very quickly, but you basically do an average of all these electron transitions, and that's the color you see. So speaking of chemicals, when it comes to colors, there's a very distinct trend, at least for inorganic compounds like minerals. And this is the periodic table of elements. And what I did was I went in and I took a mineral from the first element on each column and I placed them above their column. So like this is a lithium mineral, that's beryl, and so on and so forth. And as you can see, one group of the periodic table is way more colorful than the others. And that is this middle dent here. Scientists, we call them the transition metals. So they are the very colorful ones. A lot of minerals, all you need to do is add a little sprinkle of transition metals, and all of a sudden you got color. There are several reasons behind that. One is they just have more electrons to play with. Orbitals, they're grouped into different sizes. The ones on here, these are the s orbitals. They can hold 2 electrons. The ones on the right, they can hold 6, the p orbitals. The d orbitals in the middle can hold 10. So right off the bat, you've got more electrons to play with. And more chances of it smacking that very narrow visible light that we see. So that's why transition metals make colors. They also, unlike the other elements, they can form ions of various charge. +2, +3, etc. And these different charged ions will generally have different colors to them. Because, again, you're changing the amount and position of our electrons. And the moving electrons, again, as we saw earlier, create color. So here, it's not a mineral, but it's 4 different solutions of vanadium. And as you can see, each one of them has a different color because they have a different charge to it. Now, why does that happen? As I said, not only does it have more electrons, and so you have different, more opportunities for electrons to move, but coincidentally, when you're making an ion with transition metals that have the d orbitals, they split in half. So you got a set of Ds up here, you got a set of Ds down there, and the gap between those 2 sets of d orbitals exactly matches the visible light spectrum. So when you have electrons going between them, you generally get visible light coming off of it. So if we were to classify our minerals, we can classify them into 2 big groups. The first is called idiochromatic. So these are minerals that are always the same color. They're the easy ones to identify. Why are they the same color? Because generally they're the ones that have transition metals in it automatically. It comes from Greek idios, one's own, and chromatic means color. You'll see that suffix several times tonight. So it's one's own color. You can remember this by the phrase, only an idiot relies on themselves. And the elements that give them color are called chromophores, again, referring to color. So here we've got several examples. We've got turquoise, which is always a lovely blue, azurite, blue, malachite. All 3 of these are copper-containing minerals. On the right, we've got cinnabar, which is a mercury-containing mineral, which is again another transition metal. So if you've got transition metals in them, they're probably idiochromatic and are always the same color. On the other hand, if you're playing around the rest of the periodic table, those minerals are generally allochromatic. These are minerals that are normally colorless, but if you do certain things to them, like again, sprinkling in a little transition metal, you can make them colorful. So again, they're colored generally through trace elements, and allos is from Greek meaning other. And of course, my favorite mineral of all time, fluorite, is an allochromatic mineral. It's why it comes in a ridiculous amount of colors, because you just add a little bit of, anything to it, and it gets a color. Okay? So an example of an allochromatic mineral is corundum. Corundum is aluminum oxide. Neither of them are transition metals. And if we add a little bit of chromium to it, which is a transition metal, we get our bright red rubies. If we were to add a little bit of titanium and iron to it, on the other hand, we get blue sapphires. Yeah, and if you add various other transition metals, you get various other colors, because although people normally think of rubies and sapphires, you can get pink and green and who knows what else for sapphires. Okay. So one of the ways, so that's adding transition metals. Again, that's probably the easiest way to get a colored mineral, but there are other ways. Guys, we're going over the entire spectrum today. And one of those ways is by having a crystal defect. So I'm sure you all know minerals are crystals. They got a regular repeating pattern of atoms to them. That's actually one of the definitions of a mineral. It must be a crystal. So sometimes in your crystal, you can have some of the atoms pop out of place. And those out of place atoms can change the electron structure of the entire crystal. That's most commonly seen in my favorite mineral of all time, fluorite. In particular, the purple fluorite many times is made by these crystal defects. It's known as a Frankel defect, after the guy who found it. That is one of the hottest ways we can get minerals in color, and that is radiation. So basically what happens is radiation comes along and it smacks into the electrons. It smacks them so hard it rips them clean off of their atom. Now this happens quite a bit normally. Most of the time, those electrons just go off and they join up with another atom and everything's fine. But in crystals, you can actually get those electrons trapped. Instead of going off and rejoining other atoms, they basically become trapped in the crystal matrix. And that, again, can alter how light interferes with the crystal, giving it color. So there are several different ones that can do this. We've got amethyst, which is iron and radiation. Smoky quartz, which lacks the iron, so it's not purple. Blue topaz. Most of the blue topaz, if you're in gemstones, are irradiated. In fact, I got a really cool example of that. My bottles here actually show this property. Now, they aren't crystals, they're glass. But one of my science supply companies found a whole bunch of old bottles in a barn, and they're like, yeah, let's stick one of them under a radiation source. And that's why this bottle is purple and this one is not. Because this one got irradiated, and the electrons got basically smacked off the atoms and are just basically inside the glass here. So yeah, of course I have to have that, so that's why I bought them. Oh, fun fact about the irradiation, depending on how you do it, you can actually, oh, two more facts I need to mention. You can actually make them radioactive themselves, albeit weakly. So if you're doing this industrially, you actually will put them in a lead-lined vault for a couple months for the radiation to decay away. Most of these, no, the smoky quartz and amethyst can occur naturally just because there are radioactive elements in rocks, uranium, thorium, and the like, and over aeons they can irradiate the crystals. Smoky quartz, especially if you see it to be very, very black, generally that will have been irradiated. Sometimes it might be natural, but a lot of times the super black stuff is irradiated. Now, we can create color by using radiation to knock electrons around. We can actually reverse it if we want to, though. And all we do to undo the radiation effects is a little bit of heat. Again, the electrons get smacked, they get trapped in the crystal lattice, and if you add a little bit of heat, you can jiggle it. That's all you're doing. You're adding energy of motion to the bonds and the atoms and stuff, and that vibrations will be enough to let the electrons basically snap back to where they were, undoing the color. And you see this when you're buying citrine, mostly. Amethyst is actually a bit more common than citrine is. And so what they'll do, if you want to sell some citrine, is they will take amethyst and they will heat treat it, basically undoing the radiation effect and revealing it to become citrine, which is basically irony quartz. Personally, I think that's a crime, but you know, if you like it, for you guys. So next up, and last in our physical color section, are inclusions. I'm sure you all know what an inclusion is. They are minerals that are inside other minerals. Well, sometimes those sneaky other minerals can actually color the stone, making it look a different color than it would normally. A lot of times this happens with quartz because, you know, of course it does. So here on the left we got a sunstone, which is, I believe it's a feldspar, and it's full of tiny little copper flakes, giving it a lovely peachy orange color. In the middle we've got aventurine quartz, which is actually full of the mineral fuchsite, which is a chrome mica. Chrome's another one of those transition metals, that's why it's green. On the right we've got black feldspar, which is generally colored through magnetite inclusions inside of the mineral. Okay? So, the next big grouping of color in minerals that we're going to go over is physical color. We call these pseudochromatic. Pseudo means false, chroma means color, so they're false color minerals. So they are minerals that gain color not through their chemical structure, but because of their physical makeup. Their physical makeup generally has structures that exist on a nano scale. That's 10 to the negative ninth, or 0.000000001 scale. Why does it have stuff at the nanoscale? Because that's where the visible light is. Visible light has a nano wavelength, so if you're going to interact with it, your structures have to be on the nano scale. Scientists, we call these emergent properties. They're properties that come about because they have structures at that scale. And one of my favorite examples of that, not a mineral, but is this here. Before I was an earth science teacher, I was a chemistry teacher. And I would collect various interesting forms of the elements. And this here I thought was pretty cool. This isn't red dyed water. Believe it or not, this little bottle here cost me 70 bucks.
Wow.
Because this is nanosphere gold. So gold, if you grind it up into such tiny little particles, it actually becomes red. Because that's how it interacts with light. In fact, if you see a stained glass window and it has super vibrant red, yeah, it's gold stained glass. It was so expensive because they generally use this for research in medicine and the like. Okay, so you want to pass that around? Yeah?
Interesting.
Yep. So, how do these minerals get the pseudochromatic or physical color minerals? How do they get their color? They get it by interacting with light again. Now, one of the interesting things about light is that white light does not exist. If you didn't know that, that's the case. And actually, I can prove it to you with one of my favorite science toys. So could you guys in the back hit the lights? All of them, please.
He's coming.
Oh, it's somewhere else? Okay. By the way, those of you who are sensitive to strobe lights, do highly recommend that you close your eyes for this. Might trigger you, but for everyone else, so here we've got my nice little ball. And as you can see, it's more or less white right now. However, if I were to take my ball and swing it,
Wow.
you see, you have 3 color sensing cells in your eyes that correspond to red, green, and blue. And when you combine them together, you get white. So white is just a combination of all the other spectrums of light. We see other colors like orange and yellow and the like because they interact with those red, green, and blue cells in our eyes in different ways, and our brain interprets those signals to be like, okay, you're like 10% red, 25% blue, 3% green, oh, that's orange. So that's how our eyes perceive color. So, if we're hitting something with white light, it has every single color in it. And so, what these pseudochromatic minerals do is they split that white light into its component colors. Literally exactly like a prism does. You see, light travels at different speeds. I know we always say that, speed of light is the fastest thing in the universe. Nothing can travel faster than it, and that's true, but only in a vacuum. When you're traveling light through a substance, it has different speeds. And so if you travel past that light through 2 different mediums, you can actually get the light waves that are traveling at different speeds to pull apart, showing you the various colors of light. And that's how prisms work. And as far as minerals go, the easiest way to see this is through minerals that have dispersion. Now these are minerals that are really good prisms. The best example of that is diamond. So not only do you see the sparkly white light getting reflected off the diamond, but you can see that there are various rainbow sheens in here because the diamond is literally acting as a prism, having all those facets, like going through the air, hitting them, and then getting split apart as a prism. In fact, that's the #1 way to tell the difference between diamond and not diamond, is that not diamonds generally don't have good dispersion. So this white topaz over here as you can see, has no dispersion, even though superficially it looks like a diamond. Then we have thin films. So many minerals, like boronite, chalcopyrite and stuff, will form a thin layer on its surface. This is generally an oxide layer, because oxygen loves to react with just about anything. And it forms basically a thin and flat prism, very similar to what happens in an oil slick. What happens is, these here are wavelengths. Waves basically have the squiggly line, and if you put two waves together, and so that the tops of the waves match and the bottoms of the waves match, you can actually add the waves together, and the resulting wave will end up stronger than before. On the other hand, if you smack two waves together and you hit a high point with a low point and keep doing that, you can cancel out the waves instead. In fact, that similar process happens in your noise canceling headphones. It's just with sound waves instead of light waves. So what's going on is the light is entering the film, it's bouncing off, and the thickness of the film allows the waves to hit each other and add, creating the color. And the different thickness of the film allows you to see different colors. So if the thickness of the film is wrong or it's not transparent, you won't see it. So yeah, generally these are very, very thin. Even up to can be down to a couple atoms thick. A similar thing happens if you pass light through tiny slits. Basically, the light traveling through it will go around the slit, hit each other, and interfere with it. And if you have a bunch of them, it will generally produce a rainbow effect. In fact, that's why if you ever see a CD, their rainbow is because they've got tons of little slits in them, which are basically splitting apart the light as they travel across it. As far as minerals go, there are pretty much only two minerals that do this. One of them is turgite, iridescent hematite. So here, this gray and white picture is a scanning electron microscope view of the iridescent hematite. And you can see there are tons of teeny little straight crystals which then can split the light apart in a diffraction creating effect. The other one that does this is iris agate. So you all know that agates have lines. Well, iris agates are lines to the nth degree. On the low end, they have 400 lines per square inch. On the high end, 17,000 per square inch. And as the light goes through, it interferes with each other, breaking it apart into color. So yeah. So if we can go through lines, well, you can do the same thing except horizontally. So if your mineral forms numerous tiny thin layers that are translucent, the light can go in and get bent that way. Again, like the diffraction grating, except more like a stack of pancakes rather than thin lines. The two main ones that do this, I believe they're both forms of feldspar. We have labradorite with labradorescence, because sometimes scientists are not creative at all with their names. And we have moonstone with adulorescence, and it forms a lovely blue color. The thickness of the layers is actually what causes the different colors because you get a different interference pattern in the light going through it. Then we have play of color. This is a specific to an opal. So opals, lovely little things here, but they are, if you were to zoom in, you would see that there are tons of tiny little spheres. Basically, tiny little glass spheres, that is all opal is. And those spheres act like tons of tiny little prisms. So you have the light come in, hit the basically layers of prisms, and they are split into its component colors. Different sizes of spheres give you different colors. And we see different patches of colors because of the individual microclimate that they're forming in. Each individual part of the opal will be slightly different than the other, and will make a slightly different group of opal spheres. So the last pseudochromatic mineral type we're going to go over is scattering. So if you have a lot of tiny little particles and your light hits it, it can be bent and scattered. They'll basically get pinballed off in different directions. And different wavelengths of light do this to different degrees. Generally, the ones you're going to see are bluish, because blue is the shortest wavelength and it gets scattered the most. So like if you got blue quartz from PlayWiki, I think that's what's going on there. I can't be 100% sure, but that's my guess. You also see it in ice, which is also a mineral, and in places like the sky, which is why the sky is blue. So because the light gets basically pinballed around by the molecules in the sky, forming the blue color. Okay. Now, our last topic of the day is everything else that did not fit in any of the other categories. So, just too cool to not include, but they're just kind of weird. And the first one is called pleochromism. The neat thing is here, these four minerals, the two on the left and the two on the right are the same mineral. Same exact mineral, the one on the left has been rotated. So depending on your viewing angle of the mineral, the color will change. And that's because, again, their crystal makeup. They're crystals, as you can see here on the bottom corner here. So this is the mineral iolite. That's a lovely blue mineral. Some people say it's Viking sunstone, that the Vikings used this effect to find their way on cloudy days. Who knows? But the key thing is, you see its chemical structure, it's not symmetrical, or at least not entirely symmetrical. So as you turn the mineral, the path that the light is taking through it is different because it's going through different layers. So the key thing with all pleochroic minerals is they are not symmetrical at the atomic scale. Now, the one on the right here, that's a tourmaline. They used a tool that you can buy if you really are into this. It's called a Chelsea filter or a dichroscope. Basically, by using polarized film, you can see the different colors in the stone without even having to change it. And there are some which have the polarized films at 90 degrees, so you can basically like wipe the color up and down and see it change, which is pretty darn cool. Then there's one of my favorites. This is called color change. And yes, the thing will change color. And that changes color based off the temperature of the light. I'm sure you all have run into this with the new LEDs, but as seen before, white is not white. You can't just go to the light bulb store and pick up a random white light bulb because it will probably not match the rest of your room. Because there are different mixes of colors in that white light. Some are redder, some are bluer and stuff. And God forbid you mix them, because that one light that is not the same temperature will really stand out. Well, what happens here is in the mineral, it's got gaps in its absorption. So basically, there are two holes in it that will allow different colored light through. So if you have a light that is rich in a particular color, it's going to show up as that color. And then if you change the color of the light that's surrounding it, it will show up as that color. The stereotypical one of these, the first one ever discovered, was Alexandrite. There were some miners out in the Ural Mountains in Russia. They mined these stones. They thought they were emeralds because in daylight, hey, it's green. It's an emerald, right? Until they were looking at their stones around their campfire, and they're like, why did our stones become red? And that's because the campfire has more red light into it. And that's why Alexandrite's nickname is emerald by day, ruby by night. Unfortunately, though, Alexandrite is heartbreakingly expensive. They make diamonds look cheap. So odds of me ever getting one, namesake stone, is pretty much nil. But we're great with science nowadays. We can make our own. So obviously with such a cool thing, they have synthetic versions of it. So this is synthetic corundum that has been treated, when it grew, to have a color change effects. So I got two flashlights here. One is an LED, which has more bluish light. Other one is a incandescent flashlight. So if you shine the light on them, you should see the corundum show up different colors. So I'm going to pass that around. I highly recommend actually shining the light both at the same time because it's very obvious. By the way, if you want one of your own, you can totally buy one. I got that on eBay for $30. So don't buy the ones that are like $100 and something. They're ripping you off.
How do I do this?
Press the button. There's a black button on the side. Over here.
Oh. No, wait. Everybody's gonna get pissed off at me.
Just hold the button. Hold the button.
I like to think it died.
You hold the button down and it works. So you see it's red.
This is orange.
Yeah, well it's purpley. And now if you take the other one, so see?
Oh, wow.
Yeah.
Yeah. Ah,
Okay. So again, the black one is kind of, the small incandescent one is a little dim. You're going to have to hold down the button to see it.
I have a necklace
really
like
cool.
that from the 1900s. I
Oh, wow.
got it in the flea market. It's purple in one corner and it's blue in another corner.
Very cool, very
Yeah. It's a crystal. Yeah,
cool. You know what? If that is Alexandrite, it will be ridiculously expensive.
Yeah.
Okay, so we're at the end. So the last type of color and minerals is called thermochromic minerals. Unfortunately, I could not find a picture of this, so it'll have to do with the mood sheet up there. It's pretty much the same idea. So basically what you're doing here is you're heating up an object, and when you're doing that, you're actually changing the molecules of it. You're causing a change in shape of those molecules, and that change in shape of the molecules then changes how it interacts with light, showing different colors. Sometimes you can just bend it, hit it with heat, and it will bend. and over time it will slowly relax and go back to its original color. Other times you heat it, it will just literally break your, and it will just be that color now forever. If you're going to play around with blow torches and minerals, I would highly recommend that you know what's going to happen and be prepared for that if it does. Okay? Alright, so that is minerals and color. That's all I have. So are there any questions?
The opal crystal is a ball?
Yeah, tiny little
Amazing.
balls. Yeah, and to think that it happened naturally.
Wow. How would I see the balls? How much magnets is in it?
A lot.
A lot.
That was a scanning electron microscope.
Wow.
So basically you're blasting with a beam of electrons to see it. So yeah, it's very, very tiny. You won't be able to see it under a microscope.
An easy example to see is something similar to that is when you dig up jasper, break jasper open, you ever find those pockets where they have the juicy balls?
Yeah,
Oh,
It's the same principle. They're both crypto crystalline.
Right,
Goes
yeah.
back to the teeny little.
chalcedony.
Yep.
The blue jay they say is actually brown, and the morpho moth is actually brown.
Yeah. Well,
Is
that's
that the texture or what?
that's a pseudochromic one. You're basically using the structure of the wings of like a morpho butterfly to split the light. Because getting a blue pigment in nature is somewhat difficult. So a lot of times, especially with bird feathers or butterfly wings, you'll use the like prism effect to get that blue instead of actually trying to dye it. In fact, mallard ducks, what they do is they take blue structure in the feathers with a yellow undercoat to get it green. Yes.
The heat treated cannabis chemically, is it any different than actually brings into besides the
No.
fact that it's just
Yeah.
even if, like, because I see all the time the bird marks and. Do you want me to hold this stuff?
Well, the white underside is generally like the matrix and stuff. I think it's pretty much impossible to tell. Well, I'm sure if you know what you're doing, you might be able to tell, but it's pretty much the same thing. If you were to take, again, that citrine and shove it in a radiation source, you come out of this thing.